All right, if you think of something, jump in, okay? It's always difficult to know in this situation whether people have a question but they can't get through, or I don't know. All right, so what we're going to look at now, we've covered most of the information for the two anaerobic systems and the aerobic system. So how we mechanically produce the ATP. Now we want to look at when are we using which systems, all right? And which substrates are predominant at certain times, okay? So remember that the substrate is the thing that's being broken down to create the ATP. So which substrate is predominantly used often depends upon the availability of that substrate, how much energy that particular substrate is capable of producing, and as we'll see in just a little while, really key is the intensity and the duration of the activity that's occurring. Okay? So when we have a meal that is high in carbs or high in fat or even high in protein, although it takes our bodies longer to adapt to using protein than it does for carbs and fats. The substrate that's most available, so the one that you eat the most of, in an acute scenario, is preferentially going to be metabolized, right? So the same if chronically your diet is high in that substrate. So if you're on a high carb or a high fat or a high protein diet, then that substrate that's high will eventually be used a little more than before, right? So remember though that when we're talking about protein, 2% or less of protein is used in exercise less than 60 minutes, and that has to be continuous, 60 minutes, right? And if you're doing 3 to 5 hours, it's somewhere between 5 and 15 as a high. Typically you see 5 to 10%, so 15 is pretty high, right? Possibly. Okay. So when we're working anaerobically, then our substrates are, well, we've got the ATP there already, remember, in the first system for between 5 and 10 seconds. Then we've got our phosphocreatine already in the cell. And then we're going to use glucose or glycogen, no protein, no fats in anaerobic work. Okay? If we're doing aerobic work, it's going to be primarily carbohydrate and triglycerides that fuel that work. Okay? Depending upon the intensity, as you'll see in a minute, intensity and duration. All right? So this glucose for anaerobic work is going to come from either the bloodstream or by breaking down glycogen that's stored in the muscle tissue, right? And the carbs are stored. Triglycerides, we have a little bit of storage in the muscle, but they're stored everywhere else. And we're going to break them down, dump the fatty acids into the bloodstream, move it around to the working muscle and use it aerobically. Okay? So, our first variable of interest, like the primary variable that we want to be paying attention to here, because it's key to achieving the majority of the goals that people are going to set for their workout program, right? I want to put on more muscle. I want to get fitter cardiovascularly. I want to lose fat mass, right? Any of these goals involve getting the intensity of the program correct, okay? So when are we using fats and when are we using carbs to fuel our exercise, right? So at rest, so sitting in the classroom, sitting on the couch watching a film at night, sleeping, okay? About 1/3 of the ATP is derived from carbohydrate and 2/3 from fats, all right? And then gradually as exercise intensity goes up, so my workload gets higher, then my need for ATP, the turnover has to be quicker, right? So I've got to have ATP more readily available in a shorter period of time. And so gradually as that workload gets higher and higher, we switch to using more and more carbs because they're a smaller molecule, right? Remember, they don't provide as much energy, but they're much easier to get at than fats, okay? Theoretically, doesn't really happen because no one really works at 100% intensity, right? But theoretically, if I was working at maximal intensity, 100% of the energy, the ATP for that work would be coming from carbohydrate because anaerobic glycolysis is the predominant source of ATP at higher levels of intensity work. Does that make sense?
So I do have a question.
Sure.
Real quick. So when I'm not working at 100% intensity, most of the ATP is from carbs and triglycerides?
Yes. Probably, depending on, so you never really work at 100%, Neri, because 100% means that you're going to fall on your face, right? You can keep it up for no time at all. So if you're working, as you'll see in a little while, if you're working like 75, 80% and higher, then most of that ATP is going to come from carbohydrate. If you're out for a slower run, so it's one of your down days or it's your light intensity day, and you're going to go a little bit further, but you're going to take it more easy, then you'll utilize more fats. Probably, depending what your version of easy is. Right? Like somewhere in the next couple of slides, it says jogging is low intensity. And I'm looking at this, I'm like, jogging isn't low intensity for me. And so my heart rate goes berserk if I try to jog, all right? So I think what we're doing today will answer some of your questions because we have some very clear windows where things switch from carbs to fats and vice versa, okay? So when we're looking at this particular change, so as intensity increases, we go from using lots of fats to using less fats to using less fats to using mostly carbs, right? So a couple of reasons that happens. One is that, as we saw before, carb metabolism produces more energy for the equivalent amount of oxygen, right? Because I can get at that energy faster. More critical, I think, for us is the idea that the harder we start working, and we'll go into this in a lot more detail in in the new book, I think it's chapter 5, when we look at the muscular system. The harder I work, the more fast twitch or type 2 muscle fibers we use. and type 2 muscle fibers are mostly glycolytic and ATP PC system. They do not make ATP very well aerobically. So the harder I'm working, the more type 2 fibers I'm using, the more anaerobic ATP production we have to do. Okay? We also see a lot of hormone changes when we exercise for any period of time. So we release a lot of epinephrine, norepinephrine, and epinephrine stimulates the enzymes in the glycolysis chain. So that stimulates carb metabolism. And once I'm using glycolysis anaerobically and I'm producing pyruvate that is turning into lactate, that as the lactate levels in the bloodstream rise, it inhibits triglyceride or fat metabolism in the adipose cells. So there's several mechanisms that play a role in what we see occur. All right, so here's the first really cool thing. I love this diagram, all right? Because it makes it so simple to use the information that we understand. And yes, I know that the research on substrate metabolism and substrate use is one of the fastest changing right now. But I'm going to stick to the old stuff at the moment until I read a lot more. Okay? So what we have, and it's really an interesting tool to use, right? On the x-axis is intensity. It doesn't have to be percentage VO2 max, it could be percentage heart rate max. It could be RPE, Borg scale. It could be METs, right? It's just intensity on the x. And on the y-axis, we have the percentage of energy from either carbs or fats. Okay? So what this is telling us, the carbohydrate is the blue line, and the triglycerides is the orange line. So when we are at low intensities, all right, fat metabolism predominates. It's not that there's nothing going on with carbohydrate, right? There's always something going on with carbohydrate. But fat metabolism predominates when we're at low intensity. So when we're asleep, when we're sitting in class, if I'm walking slowly, right? So I go out with my partner and the dog, then we're walking really slow, right? So if I go out on my own, I'm walking much faster. So we shift up the graph, okay? So up to this point here, this crossover, the crossover is the point where we start to use carbohydrate predominantly, and we use less and less fat as our energy source. And that split, just as you can see, the harder I'm working, right? The harder I'm working, the more important carbohydrate is and the less important fat is. Okay? So that crossover occurs about 35% of VO2 max. Oops. Okay? So that's pretty low, right? So near it. I don't know what percentage intensity your runs are, but you're probably using a lot more carbohydrate than you are fat when you're running, typically, right? But there is more to it than just what's happening with intensity, okay? So we get this crossover, about 35%. Doesn't mean I'm not using fat. So up until sort of 60% or so, fat is still playing quite a large role, right? It's when we get into those really high intensities that we see we're not using very much fat at all, and it's almost all carbohydrate. So this is one of the things I see down in the Max Pack when people are on campus, right? I'll stand at the window and there'll be someone who is, how can I put it, I don't mean to be judgmental, but there's someone on the treadmill or on the bike who looks a little bit heavy and they're working really, really hard. So my guess when I'm watching them is that they are being disciplined and they're motivated to try to lose some weight, right? Fat, okay? But they're working really, 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 really hard. And I always feel so bad because when you're working really, really hard, you're not using fat. So they're working too hard to achieve their goal, okay? And we have some data that supports this very nicely. It's called the fat max zone. So, let me draw you this. Okay, here we go again. Come here. Okay. All right. So, oh, good Lord. Why isn't there? There's only a rubber to start all over. They should give you a rubber that lets you just take out a bit of the picture. There we go, that's better. Okay, so again on the x-axis we're going to have intensity. On the y-axis we're going to have fat metabolism. Okay? And the data that we get here when we're looking at fat metabolism looks a little bit like this. Okay? And so what this would suggest is that when I'm working at lower intensity, I'm metabolizing fat, but not very much, right? When I'm working at higher intensity, I'm metabolizing fat, but not very much. What I want is this zone here where fat use is optimal, okay?
So it's usually like 60% intensity? Or?
It is, I can give you the numbers. If you are working at heart rate max, this end of the zone is about 68%, and the top end of the zone is about 79%. Oops. Okay? If you're working at VO2, then the bottom end is around 55, and the top end is around 72% VO2 max. Right? And so this is called the fat max zone. It's the point at which, not the only time you're utilizing fat, but the point at which you are optimizing fat use, right? So if you have a client or a student in your PE class, or hopefully not, but an athlete, right, who you've calculated their body composition, and they say to you, my goal is to lose fat mass, then you want them working in this zone here as much as possible. Does that make sense? Because it's the point at which, if you go back to the crossover graph, it gets a little bit confusing because we said the crossover is occurring at 35% VO2 max, which is all the way down here somewhere, right? But the crossover occurs before you're working very hard. So what this zone represents is the combination of working hard enough to be using enough calories that are still fat, not carbohydrate. Does that make sense? Okay, so let me go back to so here, the crossover occurs at an intensity that's too low to really be using a lot of energy, a lot of ATP. So we have to bump it up into this region here for optimum fat use. Okay? And let me have a look. There was a box. Okay, box 3.6 on page 64 talks about this idea about the fat max zone as well. So we said that we had two crucial variables. The first one is the intensity that I'm working at, right? How hard am I working? The second crucial variable is the duration, the time that I'm working, okay? And so what we see when we look at, because what we need is, we need enough time for enough metabolism to be occurring to impact fat storage, right? So, or if we're trying to build muscle, we want to make sure we're not doing that much time because we don't want to impact muscle growth, which takes a lot of calories, right? So, when we look at the time variable, what we see is that if I maintain the same intensity, that eventually there's going to be a gradual shift from carbohydrate to fat metabolism as the time goes on, right? Even if I stay at the same work rate, the time plays a role because remember the reason we use carbohydrate is because it's a small molecule and we can get at the energy in that molecule rapidly, easily. But fat has a lot more energy. So if I go for long enough, I'm going to give my body a chance to start using fat stores which provide a lot more energy for this long training session, right? Or event. Okay. So if I'm doing low, moderate levels of intensity for a long time. As I said, I had to laugh because it says jogging for 30 minutes or more. And I'm like, that is not low intensity. But maybe the people that wrote this book are really, really in shape. Okay? So this happens, right? We see this gradual shift from carbs to fats. Again, because of the hormonal response to the exercise, right? The epinephrine and the norepinephrine increase the activity not only of the enzymes in glycolysis, but also the lipases which facilitate breaking down the stored triglycerides. Okay? Insulin, which is released in response to carbohydrate, inhibits the lipase. So we would see a decrease of free fatty acid availability and more carbohydrate availability in the muscles. So that's important if you're working with someone, right? Because if they ingest either a high-carb meal or they use one of those carbohydrate drinks, within 30 to 60 minutes of you giving them a training program, they're going to be metabolizing carbohydrate from that meal or that drink rather than hitting their fat stores, which is what they're paying you to do, right? So we've got to be a little bit careful there about the timing of meals or these supplement drinks. If the goal is fat loss, right? Does that make sense? So if I don't eat the carbohydrate or I don't drink the carbohydrate, then there'll be a decrease in insulin once the blood glucose has been utilized, and then we'll see this shift towards fat metabolism and away from carbohydrate metabolism. Okay? So remember we said a couple of slides ago that we'll use the substrate that preferentially that is most readily available. So if I give it carbohydrate and I raise my insulin levels, then I'm going to be using carbohydrate to fuel the exercise session, not fats. Okay? Eventually, long duration, low intensity, low moderate levels of intensity, that's longer than 60 minutes. So for example, a marathon, you can reach the point where you deplete your glycogen stores and we see fatigue, right? So you'll hear athletes say, oh, I hit the wall 3 minutes from the finishing line, or something like that, right? And hitting the wall triggers then a return to fat metabolism. So for example, what you see in marathons quite often, particularly with the untrained or the lower trained individuals, less, although depending on the environment, you don't see it as often with the top class athletes, unless there's been a switch in environment from training to the race, right? But you see it a lot with the middle and the lower level people that are running. Okay, they'll be running and they'll be plodding along at their pace, right? And they're using mostly fats, but they're chugging along, using their carbohydrate because it never really stops, and they're not topping up their carbs the way they need to during a long race. And then they know that they're getting close to the finishing line and they want to try and get a faster time, so they speed up a little bit, which means they increase their carb use, and then all of a sudden their legs start buckling, right? And some of them don't make it. I've watched races where people literally collapse in sight of the finishing line and cannot finish, right? I've seen people stop their own race and help them finish the race so that they can say they did it, right? Which is very, very generous, I think. Okay? So what happens when the legs do this is you are done with carbs. No carbs left. The liver is empty and the muscles are empty. And you have to use fat. Well, that means you've got to slow all the heck back down again, right? Just as you were trying to speed up to finish, now you've got to crawl or walk, right? Jog very slowly if you're lucky, okay? So that's what hitting the wall does. It means that I am done with glycogen. I can't produce ATP quickly anymore. I have to switch back to fat metabolism predominantly, and that means I have to slow down. Okay? So if I'm doing an event that is less than 60 minutes, it's a waste of time spending money on carbohydrate drinks, right? Water is going to do just fine for something that's less than 60 minutes. But for those longer duration events, those carbohydrate drinks, or like in open water swimming, in like a 10K open water swim, they'll have floating tables with little jelly cubes on them. And the swimmers can swim past and grab a jelly cube and keep going. Right? It's like you see with the marathon where they run over and they grab it and then they keep going. They don't stop, right? And they just chuck the cup down, and then they've got an army of volunteers to pick all the trash up. Okay? So the same idea, because you want to maintain your blood glucose levels so that you don't hit the wall and run out of carbohydrate. Okay? But less than 60 minutes, you're not going to run out of carbohydrate unless you haven't eaten any for 3 weeks because you're on the bleeding keto diet. And then you're on your own, because I warned you. Don't do it. Right? So we have another crossover graph that tells us really the same thing, just using the different variable. Okay, so this one looks like this. So here's my Y and my x-axis. And my x-axis this time, instead of being intensity, is time. Okay? And my y-axis is still the percentage of energy from fats and carbs. Okay? And what we see this time, which one was which? The carbs were blue, right? And the fats were orange. So this time our crossover goes the other way. This time, ignore the bump. So that's my carbs. And this is my fats. And now our crossover here is about 20 minutes or so on average. So now we have another piece of the picture, right? If I have a client that wants to lose fat mass, or a PE student, or an athlete, or a family member, right? Whoever, or me, right? Then I've got the fact that I have an optimal intensity range to work in to use as much of my stored fat as possible, right? As long as I don't have a carb-heavy intake within an hour of going for that walk, run, bike, swim, whatever, right? So I know how hard I've got to work. Now I know that 20 minutes is the point at which I've been going long enough to stimulate that fat use. So if I'm only doing 15 minutes or 10 minutes, I still am not optimizing my fat use, right? Because the fat, being the predominant energy source, occurs at 20 minutes, which is, I believe, one of the reasons why the health guidelines try to encourage people to get healthy enough to do a 30-minute block. Because then I'm 10 minutes past this crossover, so I've done 10 minutes of optimum fat use, and I've got some metabolic increase in metabolic rate for the next hour or so that increases fat use for the next hour or so. Right? So when we look at the guidelines and they say, well, you can do for health benefits, you can do your 30 minutes in 3 10-minute blocks. That's going to improve your cardiovascular health. So that's going to improve your risk for heart disease, right? It is not going to improve fat loss. Right? You've got to start clumping those 10 minutes together. Does that make sense? So it's really cool because now we've got all these tools to use to help someone lose weight in a healthy manner, in a way that will work, right? And if we can encourage them to continue these behaviors that they're learning for the long term, then they're not going to put that fat. We're going to get rid of this yo-yo, weight loss, weight gain, weight loss, weight gain, dieting garbage that people put themselves through, right? We know our seesaw, we know our energy balance, we know if we want 2 pounds a week, we've got to tip that energy scale, we've got to have a discrepancy of 1,000 calories a day. Part 1. We know we've got to work at a particular intensity. We know we shouldn't eat carbs before we go out and exercise within a limited period, obviously, right? And we know that eventually we want to be exercising for 30 minutes or longer without stopping. It's got to be aerobic. We have all the tools, right? It's just all the marketing people with the money make a louder noise and encourage people to spend all their hard-earned pennies on nonsense. Okay, questions on any of that before we start the next piece of the pie?
No.
No? And I think this next bit will answer some of the questions you had last week, I think it was, Miri. Kayla, any questions?
No, not today.
Not today? Okay. Because this is that stuff you're really interested in. Helping people get healthy. Okay. All right, so we're going to change tack a little bit and look at some biochemical information around that is linked with an individual's capacity for aerobic work. Okay? So we have mentioned in lab, and we've mentioned on and off a couple of times in class, that we often use VO2 max as the measure of someone's aerobic capacity. So that's true, we do, but there are some issues around VO2 max, right? It's predominantly genetically determined. So your ceiling for VO2 max is a fixed position, okay? So if you take someone who is untrained or low trained and you put them on an aerobic program, it takes, and you measure their VO2 max, we see an increase in VO2 max as they get fitter. Takes anywhere from 8 to 12 weeks for an individual to reach the plateau of their VO2 max. So VO2 max goes up, goes up, goes up, they're getting fitter, they're getting faster, this is good, this is nothing to do with weight, right? This is all to do with cardiovascular. So they're getting fitter, they're getting faster, they feel good, their VO2 max is going up and up and up, and then it hits a plateau and it stops. And that plateau, unless you are prepared to work very, very hard, isn't going to shift. And even if you work really, really, really hard, it only shifts a minute amount, right? There's this little range for VO2 max that everybody has. So VO2 max plateaus. Well, that's a little bit odd though, because if my VO2 max plateaus at 12 weeks, how come 6 months later I'm still getting fitter and faster, right? And that's where lactate threshold comes in, because it isn't VO2 max that improves after the 8 to 12 weeks. It's your lactate threshold that improves, that pays off in improved performance and fitness. Okay? So lactate threshold represents the intensity or the race pace that you can maintain. Okay? And it's technically the intensity at which your blood lactate exceeds your resting concentration. So the reason that we typically use VO2 max, not lactate threshold, is that lactate threshold involves a blood draw, which is not, it's not manageable out on the field. There's all kinds of permissions and rules to follow about blood draws, and it all gets very messy and complicated, right? So for untrained people or low active people, their lactate threshold typically occurs somewhere around 50 to 60% of their max oxygen consumption, their VO2 max. For someone who is trained as an endurance athlete, so a cyclist, a runner, long distance swimmer, their lactate threshold is much higher, right? It can go up to 80%, maybe even more than that, of their VO2 max. And that means that that person can train at much higher intensities before they reach the threshold. And you'll see why that's important in a second. So how hard can I train before we start to see lactate increasing in the bloodstream? Okay? So remember that it's not lactate or lactic acid that directly causes the acidity in the muscle cell. All right? The acidity comes from breaking down ATP and other substrates and hydrogen buildup. So it's the hydrogen accumulation, the acidity that hurts performance, not lactate or lactic acid like we get told all the time. Right? Oh, your muscles are sore because of lactic acid. Oh, you're slowing down because of the lactic acid buildup in your muscle. No, you're not. No. because lactic acid turns into lactate and gets dumped into the bloodstream. It's not sitting in the muscle getting in the way, right? It's the hydrogen ions that are causing the problem. So as our lactate threshold increases, we have a significant correlation between lactate threshold and endurance performance. Okay. So lactate threshold is often used as a training aid in runners and swimmers. I've not ever heard of it being used in another event. But runners and swimmers often will have training programs that are set in lactate threshold zones. So you're either above your lactate threshold, below your lactate threshold, or at your lactate threshold, right? So you may have heard that scenario. So what does it look like? Because it's always easier to do this stuff when you've got a picture, okay? And we're going to start this and then we will review it on Wednesday. So, don't worry about OBLA. It's more technical and I don't think it's as helpful as understanding, personally I've not ever found it as helpful as understanding lactate threshold. So if you want to know more about it, let me know and I'll find something out. But here is our untrained or low-trained person. On the x-axis, we have exercise intensity, in this case percentage VO2 max, but again it could be percentage heart rate max or RPE. And on the y-axis, we have blood lactate concentration. So our untrained person is walking or jogging along, and their lactate is not changing very much. And then all of a sudden, you go round a corner on your lactate measures and they start shooting up very, very quickly. And that corner is called your lactate threshold. What it is meant to represent, or what it's thought it represents, is the point at which you switch from using mostly fats to mostly carbs, right? Because if I'm using, or let's put it another way, from using mostly aerobic metabolism to anaerobic metabolism. So you'll sometimes see it called the anaerobic threshold. Because if I'm working aerobically, I'm not dumping blood lactate into the bloodstream. It's only if I'm using glycolysis predominantly that I'm producing lactate. So the corner represents the switch from predominantly aerobic metabolism to predominantly glycolysis. And I'm going to stop there and let you think about it for a couple of days, and we will pick up and talk some more about lactate threshold on Wednesday. Questions? Okay.